Hi guys. This is a breadboarded example of a sine wave generated from the Arduino's PWM output pins. So over here, I have a standard PWM, as you can see in the oscilloscope. It's 123.5 kilohertz. And then with the filter, which I'll explain later, so with the filter on this side of the circuit, I can measure a sine wave, or very close to a sine wave, on the same frequency, 123.5 megahertz. So basically, how it works is there's a signal source, which is this little wiggly component here, and that's the Arduino output PWM pins. So it's outputting square waves, and then I'm using an LCR filter, so a capacitor and an inductor in series with a resistor, and I'm taking the voltage out of the resistor. And what this circuit does is the capacitor will filter out really fast frequencies. So it'll let really fast frequencies pass and block uh, the slower frequencies. The inductor does the opposite, so it blocks the extremely fast frequencies and um, it lets the slower frequencies through. Uh, and there's a band of frequencies that pass both of them and reach the resistor. And that band of frequencies is determined by the resonance of the LC tank, essentially. So there's a lot that went into this actually. I'll just put uh, some example problems that I had to that I had to solve. So first of all, there's a transfer function associated with this circuit, and deriving the transfer function is not too difficult. So the transfer function defines the input, uh, the output divided by the input. So that's what the transfer function means. It's like how much attenuation happened to the signal. So the output voltage divided by the input voltage at different frequencies. So there's a S domain that's derived from basically a bunch of Laplace transforms. I'm not going to go over the derivation of the math, but essentially this acts as kind of a voltage divider. So the voltage across the resistor is this resistor is in series with the impedances associated with the capacitor and inductor. So here is basically what that means. The voltage across the resistor is going to be the voltage divided equation across the L, C, and R circuits components. And then if you take the reactance of the capacitor, that becomes 1 over WC, W being the angular frequency, and then the reactance of the inductor is just WL. So you can essentially derive the transfer function, and the thing that we care about really is the magnitude of the transfer function, because there's also a phase transform. It becomes sort of this equation here. And at resonance, you can find the resonance frequency by basically finding. So there's going to be the transfer function is going to be some sort of a graph when the frequency changes, and as some frequency, the transfer function is going to be at its highest. So it's going to be not blocking a certain amount of signal. It's not going to be blocking as much signal at a certain frequency. So if you differentiate the equation and you find the maxima, you'll find that this equation, when differentiated, it has a maximum. It has a maxima at the frequency of this. So 1 over 2 pi root LC. Essentially, what's happening at this frequency is the discharge and charging of the capacitor and the discharge and charging of the inductor essentially cancel each other out. So the frequencies at this resonance frequency essentially passes without being attenuated at all. And if you plug in this frequency into the transfer function, the attenuation is 1. The transfer function magnitude is 1, so it doesn't get attenuated. So cool. So now we know that we can tweak the inductance and capacitance to specifically allow a certain frequency to pass. And then, but then, like, what do we set for the L and C if we want to filter a certain frequency? Because like L could be really large, C could be really small, and vice versa. So to determine that, there's a couple of other things in the circuit to work out. So the first is the Q factor. The Q factor is basically how sharp you want the filtering to be. So how much of the frequencies around the resonance frequency do we want pass in the band filter? So the bandpass filter looks something like this. There's a resonance frequency that it doesn't block at all, but then to the left and right of the resonant frequency, it's gonna basically per decade of frequency, it's gonna block more and more of it. So and the Q factor determines how broad this peak is. So for example, if we let in a resonant frequency of 10 hertz, if we had a really high Q factor, then it'll only let in 10 hertz. So this peak will be very sharp. Whereas if we had a low Q factor, like in the decimals, like 0.01 or something, it'll let pass like frequencies that are pretty far away either side of 10 hertz still. And that's the Q factor itself is a number determined by the resonant frequency divided by the basically the range at which the signal was attenuated by 3 dB, which is 0.707. And we need to determine what Q factor is acceptable, because the Q factor is also equal to this equation, which I won't derive, but it's essentially another relationship between L over here, and then C is actually captured within this resonant frequency factor, and also the resistance. Something that's strange to me at first was that it seems that as we increase the resistance right here, the Q factor actually decreases. So that's kind of strange. It's like, why is it that when I increase the resistance of this circuit, that it ends up allowing more current through, ends up allowing more voltage through at different frequencies. And the reason it does that is because this is actually a voltage divider. So you can imagine these two being like offering some sort of resistance to the circuit, and then this resistor here is the voltage divider that tries to capture as much of the remaining resistance, as much of the resistance as possible. As much as the voltage as possible. So if you have a high resistance over here, you actually capture more of the voltage in the entire circuit. And that's why if you increase R, this Q factor decreases and it allows more of the voltages away from the resonance frequency through. So cool. So now there's a Q factor, and then so for me, at first I wanted to just use the Arduino's the Arduino's output PWM pins native analog signal frequency, which on my Arduino Mega 2560 there's a maximum of 980 hertz. But it turns out that I don't have the capacitors and inductors necessary to actually filter that. To filter 980 hertz requires quite large inductors and capacitors, so I just don't have that. So I had to actually overclock my Arduino in order to filter in order to generate a PWM signal that is of a decent frequency. So I chose 125 kilohertz, and I'll show you how that works in the code, how to generate something like this. And so there's a PWM of 125 kilohertz, and that's going to be the resonance frequency that I want to pass. Because what happens is with a PWM wave, it's actually because of the Fourier series transform. Um, any wave is comprised of a number of sine waves at different frequencies, essentially, at different frequencies and at different offsets. So what happens with a square wave is that because it's a regular interval, the waves consisting, the sine waves which make up that square wave, are going to be the odd harmonics plus the fundamental frequency. So the fundamental frequency is the frequency of the square wave, and then every odd harmonic after that, when it gets added together, it becomes the square wave. Um, it's quite intuitive actually, because you can't have other frequencies that are not the harmonics of the fundamental. Otherwise, it will not be a regular occurring square wave if you sum everything up. So yeah, so that was quite intuitive to me, and I just needed to let the fundamental frequency through, and I needed to make sure that Q was large enough so that the odd harmonics doesn't get passed through. So the first harmonic, the fundamental, is 125 hertz, and the second odd harmonic is the third one, which is 375 hertz. So my Q factor just needs to be large enough such that it attenuated the third harmonic onwards. So I picked a value of 2.6 for this one, because it worked really well with my capacitors and inductors. And so essentially what I ended up doing was, there is a requirement for the resistance, because if the resistance is too low, the resonant frequency current, which won't be attenuated by the LC filter, it will result in a current that's too large and will burn my Arduino. So I picked a resistance of 100 ohms, which is going to be within the right current range. And then based on sort of these two equations, the resonant frequency calculator and then the Q factor, I picked a inductor of 100 and an inductor of 330 microhenries, and then a capacitor of 6.82 nanofarads. And this resulted in a Q factor of 2.6 and a targeted resonant frequency of 106 kilohertz, which it should allow my Arduino first harmonic frequency through and block everything else. And the results are pretty decent. So as you can see, so this is my capacitor over here and my inductor over here. And if I take the voltage across the resistor, just put it there, you can see that the sine wave looks pretty good. Yeah, there you go. Cool. So largely, I just want to go over quickly what the Arduino code looks like to generate something like this. Because what happens is when you use analog write, there's a timer within the Arduino. There's a variety of timers. In the Mega 2560, there's actually 6 different timers. But it doesn't run at the clock speed of the timers, because it has to leave some of the clock speed to set the PWM cycle itself. So even though 980 hertz is the maximum that you can get out of analog write, it's not the maximum that you can get out of the pins if you use the assembly. So that's essentially what I did. What I'm doing here is I'm setting pin 11 and pin 12, which is dictated by these two registers. And then basically this TCCR1A register, when you set certain bits in that register, it tells the Arduino's output pin to essentially what happens when you put in a timer. What happens when the timer reaches a certain check value. So like the check value is these two registers here, and then the timer will basically tick, and the timer ticks at 16 megahertz for this particular Arduino. And every time it ticks, it goes and checks these two registers, and if its value is equal to this value, then it will read the 6th bit of this register and determining and basically, like, if the 6th bit is doing something, then it's going to, if the 6th bit is present, then it's going to flip on pin 11, and this one is, I believe, the 4th bit. If the 4th bit is present, it turns on, it toggles pin 12. So that's what this instruction is doing. These two instructions, this is a timer register. It's a register that sets the properties of timer 1, I believe. And this is also another register that sets the properties of timer 1. But the bits in this register do different things. So in this instance, the 3rd bit, I set that because it's a bit that determines if the timer should reset if it hits the check register. And so I set that to be true, which means that basically the timer will just stay at 0 because it starts the loop, it hits 0, it checks, and then it resets itself back to 0 immediately, because it's met the checking condition. And then these two are basically prescaler values, and I prescaled this to 0, 1, 1. So these two bits, I think it's the 2nd bit and the 1st bit. Yeah, so it's the bit 0 and bit 1. 0, 1, 1 defines a 64 prescaler. So what that means is, instead of basically running this check condition every single tick, it divides the time by 64. So in the end, I get 125 kilohertz instead of an 8 megahertz. 8 megahertz PWM signal. And yeah, so that's what this Arduino code does. And you can see that there's actually no code run in the loop because everything is just set on setup, and it actually doesn't use the CPU. The Atmel Mega 2560 chip, it has all these like hardwired instructions that checks for certain registers, which on a MCU is actually just a block in memory. So it checks all these register values and automatically like triggers hard-coded instructions to flip the pin on and off. And yeah, so that's it.